The title of my talk is the diagonal hopping dependent IT characteristic of periodic DNA molecule. I'm Efta Yudiarsah from Departemen Fisika and MIPA Universitas Indonesia. The motivation of my research is the hope that we can use DNA as an active element in biosensor, and then also we can try to use it as a template for building nanowires. However, the electrical conductivity of DNA is kind of confusing. It can span from insulator up to proximity-induced semiconductors, and then why DNA has such weak properties is because probably different group doing the experiment, they use different sequence, and then DNA is soft materials. It can move internally so quickly, and then probably the medium where DNA is entered to play, and even one base pairing mismatch can change the property of DNA. And then usually people study DNA theoretically using a single channel effective tight binding Hamiltonian models. And in this model, they assume that electron can hop from one base to the others as a cosine function of twisting angle. And then in this report, we will use two-channel model, and then electron hopping following theory of Stater-Foster. And then the focus of this paper is in the exponential terms in the twisting motion dependent diagonal hopping of the molecules. Then this is the model we use. We model the NA molecule with this two-channel model. This is the basis, the NA basis, and then the top one in this circle is representing backbone. And in this model, the NA sandwiched in between two metallic electrodes. This is the left electrode, and then this is the right electrode. And in this model, electron can hop from electrode to the NA to these paths, and then electron can hop intrastrand following this path, and then interstrand this path, and then also in between two concentric base pair following this path. And the tight binding Hamiltonian model of DNA is can be represented as follows. This term is on-site energy, and then this one is hopping in between interstrand hopping in between two concentric base pair, and then this is the intrastrand hopping. This term is representing that electron can hop from one base to the nearest backbone. Oh, sorry, this is the on-site energy of backbone, and then this is that representing the electron can hop from backbone to the nearest base or vice versa. And then in the model we include that twisting motion of the base on-site energy following this formula, and then this is the base on-site energy at the statics, when it is static, and then this is the effect of torsional motion. And then after doing the mathematical expansion from Slater-Foster's model, we end up with this equation. This is the intra-strand hopping constant, and then this is the inter-strand hopping constant. And then here we will focus on the effect of this term. So we vary this term to see what effects we will get in the IP characteristic of the DNA. And then in the model we assume that backbone on-site energy is distributed normally in between this number d minus w and then d plus w, with w representing the disorder in backbone on-site energy, and then this is the backbone on-site energy without disorder. And then in this model we assume that the twisting angles has average 0 following Gaussian distribution function with standard deviations following this formula. And then we calculate the transmission probability using transfer matrix method. Using this method, if we know the wave function at site I-1 and I, and then we can calculate wave function at site I+1. And then after we do many calculations, we can end up with if we know the wave function at the left side of the DNA, and then we can calculate the wave function on the right side of the DNA. From this calculation, we can get the transmission probability, and then in doing the calculation, we employ transfer matrix and scattering matrix method simultaneously. Because if we use only transfer matrix method, then the calculation is not stable numerically. And then from the transmission probability, we can calculate current using Landauer-Huttiger formalism with this formula. And then in the calculation of current, we assume that potential drop in between the two electrodes symmetrically. Then the result of our calculation, we calculate this one. This is the characteristics of poly-DC DNA molecule with the backbone the disorder 0.1 eV, and then at temperature 4.2 Kelvin for various diagonal hopping constant. And then when we see that we increase the beta on the intra-strand hopping constant from 0 up to 6, and then we see that at low voltage, the influence of this beta is really weak, and then but at higher voltage, the influence is much stronger than at lower voltage. And then we see here there is a gap in this region. This gap is come from that we have a band in the probability transmission probability, and then in between two bands there is a gap. That's why this gap is represented here as so up here as a plateau in the IP characteristic. And a similar trend we observe if we use a lower twisting frequency. The first one is 4, and then we take 0.5 milliev. However, we see that the influence of increasing beta is much higher than at higher frequency. If we compare the IP in the higher frequency with the higher frequency, and then lower frequency with the current at lower frequency. And then we also doing the calculation for temperature 30 Kelvin, and then we observe similar trend with the 4.2 Kelvin. And then as before, the influence is stronger, but here we see that at this temperature, we see there is a profile change in the IP characteristics. As a conclusion, that we found that at low voltage, the magnitude of current is not influenced much by the change of diagonal hopping terms. At higher voltage, current increase by increasing diagonal hoppings, and then higher twisting of frequency, so weaker influence of diagonal term on the current. And then we see that we do the calculation for several temperatures. We see that these trends are observed at all temperatures we use in the study. Thank you. Oh, sorry. I would like to thank to Mr. Daniel Sandro and then BPD FIPAUI for place we use the calculation, and then the funding from DT through POPT batch 2016. Thanks.
Okay, thank you, Sandra. Nice presentation. Now, time for questions. Any question there? Maybe Mr. Ibnu? On Ibnu? No question? Pak Julio?
Cik. Assalamualaikum warahmatullahi wabarakatuh. Thank you for give opportunity to me to give a question. I want to ask about the model of tight bending DNA. May Mr. Efta can give explanation what the material in the DNA. Okay, thank you. Assalamualaikum warahmatullahi wabarakatuh.
So we back to the model. DNA is the structure of DNA is the double helix, twisting to double helix, and then in the DNA there is nucleophile base. DNA consists of 4 nucleophile bases. This is guanine, cytosine, and then thymine and adenine. But in this study, since we use poly G, poly C DNA molecule, we have only this base and this base. And then this the green circle is representing guanine base, and then blue circle cytosine base. And then in each basis, we assume there's only one state. So from this construction, we have a Hamiltonian model in the tight binding term. This is the on-site energy of electron at base, and then this is the on-site energy of electron at backbone. And then these terms represent that electron can jump from one base to the others in Watson-Crick pairs. Is based in this from this picture that electron can jump from this to this. This is what we call by Watson-Crick pairs. So electron can hop from here to here. Electron can move from this base to this. This is what we call by intrastrand hopping. And then this is what we call by interstrand hopping or diagonal hopping. So this is the terms. So what I show you before. This term is representing that electron can move from one base to the others, intrastrand or interstrand. And then in this model, the electron can jump, can move from one base to the backbone, sugar phosphate backbone, but electron cannot move from one sugar phosphate backbone to the others. Do I answer the question?
Okay, thank you. Any other questions? No? If no, we give an applause again to Mr. Musa.